Hello, today's topic is geometry optimization. Optimization is an important question in general. You might want to optimize the return on your investments in the bank. You might want to optimize the best way to get to work with minimal traffic. Optimization comes up a lot in scientific computing, where a lot of times we have a mathematical function which may be very complicated, multi-dimensional function that we're trying to optimize. And in quantum chemistry, there are several types of important optimizations. Usually, we're talking about optimization of a molecular geometry to find the so-called equilibrium geometry, where all the bonds and angles and torsional angles are all at their best possible positions. But just to set the stage a little more generally, we may be looking in quantum chemistry for stationary points. Those are the points on the multidimensional energy function where we get a zero gradient in all directions. And of course, the potential energy surface is a function of 3n minus 6 internal coordinates, or 3n minus 5 if it's a linear molecule. And we may be trying to find the equilibrium geometry, or possibly a transition state, which is still a stationary point. You have zero gradients, but in a transition state you have exactly one coordinate at which you're at a maximum instead of a minimum on the potential surface. We could more generally just be looking for a minimum of some kind of loss function or error function to find good parameters if we're fitting our own force field, for example. And we've talked about a lot of electronic structure methods that are variational, like Hartree-Fock or density functional theory, or multi-configurational self-consistent field or configuration interaction, where the energy is always an upper bound in variational methods to the true energy. So we're trying to minimize the energy to hopefully get as close as we can towards the true answer. And a lot of those variational methods, we wind up casting those as a matrix diagonalization. But the first of those points, minimizing the energy as a function of nuclear coordinates, is our main focus for today. Now, there are a number of methods for geometry optimization, and I'll just outline some of them briefly. The first thing that you might think of doesn't work well at all, which would be to say, well, I've got an energy that's a function of several coordinates, so what I'm going to do is just minimize in one of those coordinates, and then minimize in the next coordinate, and then minimize in the next coordinate until I've run through all the coordinates. And this typically won't work at all, because your energy function is normally a function of all those coordinates in a way that they're all coupled to each other. So if you minimize along one coordinate, then you spoil progress along other coordinates, and you can never find your way to the minimum. So we'll talk about some more general approaches. Most methods that are available assume you have a so-called analytic gradient. That means you have a formula for it, and you just implement that formula in the computer program. If there are no analytic gradients, either because nobody derived the equation or nobody ever coded it up in whatever program you're using, you can still compute the gradient, but you'll be estimating it numerically by moving the geometry plus and minus along different coordinates, getting the energy at each of those displacements, and then taking a numerical derivative like delta y over delta x. Some methods, on top of assuming you have a gradient, also assume you have a Hessian, the second derivative of the energy with respect to the nuclear coordinates, or at least some approximation to the Hessian. Now, the first method I want to mention, which is a very famous method, is steepest descent. In steepest descent, what we do is we find out what our gradient is, and that tells us what direction we want to go in. And then how far do we go in that direction? Well, we step in that direction until we get to the minimum energy. And often that means you'll have to go a little too far, realize your energy is going back up, and then backtrack a little bit. That's called a line minimization, if you walk in a line and go back and forth until you figure out where the minimum along that line is. And you can see this in this diagram of a contour diagram, where on the far right I've got an arrow showing me that I'm walking in the gradient direction, and then I stop walking when I hit the minimum that's in that direction. Now when I get to the minimum, what do? I just repeat. So then I get a new gradient. You can see in the diagram the new gradient is perpendicular to the old gradient. Then I go in the new gradient direction. How far do I go? I go until I minimize in that direction, and then I stop, and then I repeat, and I take another step and another step. And frequently this will get us to the minimum, but you can notice in the diagram that I've got kind of a zigzag sort of shape where I'm kind of spoiling some of my previous progress in each future step with this zigzag motion. So that's not ideal. Now there are various improvements on steepest descent. One of them would be conjugate gradient methods. And what they do is they try to avoid this zigzag nature that happens frequently in steepest descent. So what you do now is very similar. You do line minimizations in the gradient direction, except now you tweak it and you say, well, we won't exactly use the gradient direction. We're going to use a linear combination of the current gradient direction and the previous gradient direction. And the weighting for those is determined by some formula that different people have different approaches to. The one I'm showing on this slide gives you a weighting factor that is a bunch of dot products of the current gradient with the difference between the current gradient and the previous gradient. So this will give me some direction that I can go in d sub I, and then I'll do what I did before. I'll walk in that direction with the line minimization and know where to stop. But by feeding in a little information from the previous step, it tries to smooth out some of those zigzags. Now, a different way to approach minimization would be to try to create a Taylor expansion of your potential surface. If we do that, we'll invoke Newton-Raphson methods. So I could expand my energy as a function of the geometry x, and that would be the current energy wherever I'm at, x0, plus a gradient term, g, and the size of that will depend on the difference between where I'm at now, x0, and where I'm looking to go, x. And then I could go to a second order term, which would involve, since it's the second derivative, a Hessian, h. And again, that would also depend on the difference between our reference point x0 and then where we're thinking about going x. And in principle, you could go to third order, fourth order terms, but those become unwieldy. Now, if you take this Taylor series expression and you try to ask the question, where am I going to find a minimum, then I'll set the derivative of this Taylor series with respect to x to 0 and try to find that x where that would be 0. And I rearrange and do a little bit of algebra, and I find that my step size, x minus x naught, ought to be in the negative gradient direction, so negative g. So I'm going downhill. And then how far do I go? Well, it depends on how big the Hessian is. You could imagine if I have a very steep potential, then I want to take a very small step. Whereas if I have a really wide potential, I might want to take a bigger step. And the inverse of a Hessian will tell me how big a step to take. In this case, my equations will work just fine for multi-dimensional surfaces because g will be a vector giving me the gradient, the x, y, and z gradient of each atom. So it's a 3n sized gradient. And the Hessian will be a 3n by 3n matrix. And so all the relevant variables are included here. Now, if you diagonalize the Hessian to get the so-called normal modes, then we could call the normal mode vectors u sub I and the eigenvalues epsilon sub I. In this simplified case, the Newton-Raphson step in terms of normal mode coordinates is very, very simple. because the inverse of the Hessian becomes the inverse of the diagonal elements, and we sum over all the elements. And so we just step in the negative direction of the force along each normal mode coordinate, negative f sub I, times a unit vector in that normal mode direction, u sub I, and then divide that by the eigenvalue. So that's actually quite simple in the case that we do have normal mode coordinates. Now, we're talking about normally about going downhill in a direction to minimize the energy, which is equation 3. However, if I were to have negative eigenvalues, so that would be cases where I have a curvature that's sort of this way, like I'm going up a hill, directions of negative curvature will give me negative epsilons, and so then if I divide negative f sub I by epsilon sub I, which is negative, I get a positive value. And so we wind up actually going uphill if I do Newton-Raphson and I find myself in the vicinity of the top of a hill instead of in a concave sort of region of the potential surface. So this can give me a lot of problems if I'm trying to find a minimum, and unbeknownst to me, I happen to be in a region of the potential surface where I am near one of these hilltops. Then the procedure is going to do exactly the opposite of what I want. I'm actually going to start marching uphill. So the code can detect that this is happening, and it may tell you, something like the Hessian has the wrong local structure, meaning it's detected it has a negative eigenvalue instead of all positive eigenvalues. If that happens, one simple procedure is just to use a so-called level shift, where I just subtract some number lambda from the denominator, and I can force things to turn positive again, and that frequently can fix things. That's good as a sort of a fail-safe. The other thing you could do, which is much more annoying for the user, is to give up and restart the optimization somewhere closer to the local minimum. But of course that involves a lot of labor, and it's easier if we can just tweak the code and sort of nudge it away from these hilltops. Now, we've said that in Newton-Raphson we need the Hessian, or at least an approximate Hessian. So how can we get the Hessian? Well, again, it's the second derivative of the energy with respect to the nuclear coordinates. And the energy we're talking about is either a force field energy, if I'm doing molecular mechanics, or the electronic energy from the electronic Schrodinger equation if I'm doing quantum mechanics. If you're doing quantum, you can imagine computing the second derivative of that energy with respect to pairs of nuclear displacements could be very, very costly. And in fact, it costs as the scaling is on the order of n cubed, where n is the number of atoms. So this is a pretty costly calculation. We could instead just approximate the Hessian. And there are various techniques where there are tabulated values for various kinds of coordinates, and we can just look those up in a table and form an approximate Hessian appropriate for our molecule. That is likely to work fine if I have a boring, well-behaved molecule like water or methane or some hydrocarbon. If I have a really unusual bonding situation, then probably it isn't covered by what's in the tables, and so that might be a bit more suspect. I can improve the Hessian as I go along if I have an approximate one by various techniques. Every time I take a step, I can get a new gradient, and I can build up that gradient information to get a more accurate picture of the Hessian. And there are various ways to do this. The so-called BFGS approach is a pretty popular and effective one. Now, what coordinates are we going to work on when we do our geometry optimization? In principle, I don't actually need all three n coordinates because I know the potential surface is invariant to translations and rotation, so I really need more like 3n minus 6 coordinates. If I try to just use plain Cartesian coordinates, all 3n of them, it's not very effective at all. You'll have a terribly inefficient geometry optimizer. Using some kind of internal coordinates are much better. There are so-called z-matrix coordinates, which are a kind of internal coordinate, and these were popular some time ago for inputting geometries into quantum chemistry programs. Z-matrix coordinates are really not particularly effective either in geometry optimization. What one wants to do is some kind of internal coordinates, either simple internal coordinates like different bond stretches and different bond angles or torsional angles, or symmetry adapted combinations of simple internal coordinates. And there are various definitions of these: natural internal coordinates, redundant internal coordinates. These are all much more effective than trying Cartesians or z-matrices. Now, of course, if you have a large complicated molecule, it might not have just one minimum, it might have multiple minima. Some flexible organic molecules might have a number of minima, and then we could get into the game of conformational analysis, trying to figure out what those all look like. Thermodynamic properties, of course, need a Boltzmann weighting of all the relevant low energy minima. So if you do have flexible molecules, this becomes an issue to not just focus on one global minimum, but to also find the relevant nearby low-lying local minima. Finding all these can actually be very hard. So if you do have molecules where this is an issue, it can be a challenge to find them, to get the thermodynamic properties correct. You would either need good initial guess geometries or some more sophisticated approach to globally search the potential surface, either molecular dynamics and analyzing the trajectories from that, or genetic algorithms, or Monte Carlo methods, or so-called simulated annealing, which is a kind of molecular dynamics where you heat the system up so the atoms can bounce around and explore the potential surface, and then you cool it down so that then they settle into the different local minima that have been found. Occasionally, a user wants to do a constrained optimization. That's one where you want some particular coordinate to be fixed, and then you want to optimize along all the other coordinates. This can be relevant, for example, if you're trying to come up with a torsional potential and you want to get good quantum mechanical values for what that torsional potential looks like, and then you're going to use that data to parameterize a force field. So if you want a torsional potential, you've got a torsional angle, and you want to fix that and then optimize all the other coordinates and get the energy. Then you want to change it to some new value and then re-optimize all the other coordinates. And so that at every torsional angle, you want the optimum geometry in all the other coordinates. And that's what you would do in a constrained optimization. Mathematically, it's simple enough to write this. All you do is use a Lagrange multiplier technique where you write some Lagrange function, which is the original function, the potential function, and then you subtract a Lagrange multiplier times a constraint function. And we can minimize that Lagrange function and find the minimum of that, and that will be the minimum of the original function subject to the constraint. A technical problem is that not many quantum chemistry programs have an extremely robust implementation of constrained optimization, so your mileage may vary. Now, of course, sometimes we want to find the transition state instead of the minimum. If we want to compute barrier heights or reaction rates, we need the transition state. You can use an eigenvector following approach to do this, and you just make sure that the code is going uphill in the direction of that lowest Hessian eigenvector, and then downhill in all the other directions. One potential complication is that your Hessian needs to be the right Hessian so that you have exactly one negative eigenvalue, and you want to make sure that the negative eigenvalue you have is the one that points uphill in the direction you're trying to go. If you're in some random area of the potential surface, you might actually have a negative eigenvalue, but it's pointing off in some other direction that has nothing to do with the transition state you're trying to find. So for this reason, you really need two things. You need a good guess for what the geometry of the transition state is, so you're in the right region of the potential surface, and you need a good guess for the Hessian, so that it has an accurate structure that reflects what the shape of the potential surface looks like there, and that you can have an accurate direction to go uphill in. Even worse than this, on top of those two requirements, you also need a theoretical method that isn't going to fail on you as you're trying to find that transition state. Sometimes transition states can involve bond breaking or bond making, so you have very stretched bonds, and that can be a real challenge to some of the standard electronic structure methods like Hartree-Fock or MP2. They can break down if you have really stretched bonds. And so that's something you have to watch out for. You have to make sure the calculation has converged. You have to make sure the calculation has converged to the right state. There are multiple solutions to the electronic Schrödinger equation. We might accidentally land on the wrong one. And so we have all these things to worry about. So transition states are hard. There are a number of very interesting papers in the literature giving proposals of improved algorithms for how to more robustly find these transition states. They're named all kind of things like growing string methods or freezing string methods, nudged elastic band, etc., etc. These are all great, but unfortunately not all of these methods, or in fact really not many of them, have been implemented into standard quantum chemistry programs so that they're easy for users to use. My students have played with these on occasion when we're trying to find transition states, and although they really look good on paper, a lot of times in practice they don't live up to what you hope. So it really is just a challenging issue, and the user has to gain some familiarity with all the tools, and more importantly than that, just some expertise to know how to manage the calculations. So let me conclude with an example geometry optimization, just to outline the procedure and show you a couple snippets of what you can expect to see in the output file. So here's a very simple input file for the Psi4 program, where I'm using a Z-matrix specification for the water molecule. I haven't put in the charge and multiplicity, so the program will assume that it's a neutral molecule and that it's a singlet, which is fine. That is what water is. The first line in the molecule section is just the oxygen atom. The next line is a hydrogen atom, and then it says it's bonded to atom number 1, which is the oxygen atom, at a bond length of 0.98. I'm just guessing. That's in angstroms. I'm thinking that an OH bond is a little less than 1 angstrom. I don't remember exactly how much. So I'm just putting in a hopefully reasonable guess geometry. Then we have one more atom, so that's the next line. It's also a hydrogen. It's also bonded to atom 1, the oxygen, at the same bond length, 0.98. And then it forms a bond angle between it and the oxygen and atom number 2 at a bond angle of, I don't know, I think it's around 105 degrees. So I put in 105.0. And that's my guess geometry. Hopefully it's in the right ballpark. It couldn't be off by a whole lot. And then finally I just give a basis set, and then I say optimize SCF, which will be interpreted to mean Hartree-Fock here, and then the program will go do that. Now I haven't told it to compute a Hessian, and most quantum chemistry programs won't compute the Hessian explicitly because that's costly. So it will use lookup tables and guess a Hessian, and for something like water that's well behaved, the guess will be fine. All right, so now we'll just say a little bit about what happens next. The program goes off and gets a Hartree-Fock energy. Then it computes the gradient of that energy with respect to the nuclear displacements. And that gradient vector, as we mentioned before, is a vector of length 3n because I can perturb each of the n atoms in the x, y, or z direction. And then the program will print out that gradient, usually in a table where it labels x, y, and z along one direction, in this case the columns, and then the atoms in the other direction, in this case the rows, and I've got 3 atoms in this case, so there are 9 elements. And if I look at this, you notice that the molecule has a gradient that's symmetric. Oxygen is the atom 1, and you can see that it's got a gradient of negative z, but no gradient are the in the x or y directions, and that's because it's lying along the z-axis. And so if it's lying on the z-axis, then there's no particular reason why it would want to be shifted in the x or y directions, because this is a symmetric molecule, and things on the x and y directions are identical to each other in H2O. And so the oxygen doesn't feel a gradient in those directions. If I look at the next 2 rows, the 2 hydrogens, again, they're symmetric. They have their y values of the gradients are negative of each other. So one is going in one direction, one going in the other direction, but it's symmetric because the hydrogens are the same. And then they're both going, in this case, looks like up on the z-axis. And so that's the kind of symmetry you want to see if you are optimizing a symmetric molecule. If I had a symmetric molecule and the gradient was completely non-symmetric, that would be a sign that something very strange was going on. Most programs are going to compute these in Hartree per Bohr, so those are the units that we're looking at here. Just in terms of numerically, I'm seeing gradients of 1 or 2 or 3 times 10 to the minus 2. That's a pretty big gradient. It's not a crazy large gradient, but it's pretty big. So I'm really not particularly near the minimum, but I am close enough that I think the optimization is going to work. If I saw something like negative 0.5, I'm probably so far off that I could have a lot of trouble optimizing that molecule. If I converge things really tightly, I want at least 3 or 4 or 5 zeros in those gradients, depending on how precise I'm trying to be. Now, the optimizer is going to take that gradient and it's going to convert it from Cartesian coordinates into the internal coordinates. So it's going to see what's the gradient of those 2 OH bonds, and then what's the gradient in the angular direction. It'll compute a force along each of those coordinates, and then based on the force and the guess Hessian, it'll compute a step size in that direction, and then it will take a step and it'll change the geometry of the molecule. So here's just a printout of that process where I'm showing the coordinates that I guessed. Those are the previous ones. The forces, and those forces, I guess in this case, are actually in SI units, so they're attajoules per angstrom or something, or degree. And notice again the forces are symmetric, and I've got the same force in each OH bond, and then the angle has a much smaller force. And then based on those forces and the guess Hessian, we compute a change that we want to make in those bond lengths and bond angle. So you'll notice we're going to try to decrease the bond lengths from 0.98 down to about 0.94. So they were a little bit too long at this level of theory. And then similarly, the bond angle, which I thought was a pretty good guess at 105, at this particular level of theory, it thinks it needs to step it down by 1.7 degrees or so down to 103. Now 103 is actually a shorter or a smaller angle than the true angle, and it may be overstepping, but also remember we're doing this at an approximate level of theory, Hartree-Fock with a CC-PV-DZ basis, and so the right answer at that level of theory might actually underestimate the true bond length by a little bit. Now, every time you take a step, then you're going to recompute the new gradient at the new geometry. You'll update the Hessian with the gradient info that you computed, and then you just iterate this procedure. You take a step, you get a gradient, you take a step, you get a gradient, until you decide that you're converged. The Sci4 program prints each of the summary lines that I'm showing here from a geometry optimization with the little tilde after them, so you could grep it out of the output pretty easily. And you'll see that this particular optimization only took 4 steps, which is pretty good for an optimization. It's normally going to take you more. And you can see that the energy in Hartree is decreasing each time. We've gone from negative 76.0247 down to negative 76.0270. So we've decreased by a little less than 3 millihartrees, which is not bad. The next column just shows me how much the energy changed each time. Of course, the first step, there is no change. You're just starting on step number 1. The next column shows me the force, and so I see the force is going down, 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 down. That's a very nice pattern. We like that. That's the maximum force. The next column is the root mean squared force. It's also going down, 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 so very pleasing. The max displacement is what's the biggest change in the geometry that happened. And you notice the geometry is changing by less and less and less. And then finally, the root mean squared displacement. So all of these are very, very nice. In your geometry optimization, you probably won't be so lucky. You might see that max force or the max displacement or even the energies occasionally bounce back up and then go down. And sometimes that's necessary as the code is trying to figure out what the true Hessian really is. It's just working off guesses. So occasionally it'll take a step size that's too large. And then it'll realize on the next step, oh, I messed up, I went too far, let me back up. And so it is iterative. That's all I really want to share, except a couple final practical comments. Your biggest problem in optimizing an equilibrium geometry is if your guess is just way far off. And I normally mean the guess for the geometry. The guess for the Hessian can be far off, and you a lot of times can recover from that if you're doing BFGS, which most of the codes will do. But if your guess for the geometry is very far off, you can just wander the potential surface and the code can have a hard time ever catching up. In particular, if I have a molecule that's really squeezed together and I have really, really short bond lengths or very, very tight bond angles, the forces can be so large that I can just explode, and by the time that happens, the code can't recover and the atoms are just flying away from each other, and the next step just won't be able to get you back. So watch out for feeding quantum chemistry codes totally unreasonable geometries. It's normally easy enough to get an approximate geometry from molecular mechanics or something, and then those ought to be okay for quantum chemistry. If you're doing something like WebMO, if you just do cleanup geometry, you'll probably get something that's acceptable. But if you just freehand draw something in WebMO and forget to do the cleanup, then you could have just outrageous bond lengths, and it may be too much. Another possible thing that can happen is if you have a really flat potential surface, like in van der Waals dimers. If I had 2 methane molecules, they don't attract each other by very much at all. And so if I ask the program to tell me the optimum configuration between these 2 methanes and the optimum way to spin all the hydrogens, that's very hard to do because the potential surface is very, very, very flat. And so a lot of times you need to take maybe a large step to get from some bad region to a slightly better region, but it's hard to take a large step because your gradient is going to be very, very small. And so those are quite a challenge. And there are some specialty geometry optimizers like geometric that try to use special coordinates to improve this for you, but it can be a challenge in general. All right, I think that wraps up our discussion of geometry optimizations, and I think they will work pretty well for you in general, especially if you give them a good guess. The potential challenge might be transition states, and those just require a lot of patience.